Now, if you're talking about an oscillation, what comes to mind is generally something that looks like this, where it has that characteristic wavy pattern like this. Now, if you have an oscillation that looks like this, where the amplitude remains constant, as indicated by these two pink colored lines here, this one is an oscillation with no energy loss. When there's no energy loss in your oscillation, your amplitude generally remains constant. Okay, this is what we call an undamped oscillation. But in real life, you very seldom will have an oscillation that looks like this. More often than not, you will have an oscillation that looks like what you're seeing on the left-hand side here of your screen, where you notice that that object oscillates or that system oscillates, but its amplitude gradually reduces with time. So in cases like this, if you see an oscillation whose amplitude decreases, this one means that the oscillation has energy loss, which caused the amplitude to decrease in the first place. So when your oscillation has energy loss, it is actually called a damped oscillation. So damped oscillations are just simply oscillations in which the amplitude and hence energy tends to decrease exponentially with time due to the presence of damping forces. Your damping forces are actually your resistive forces. Damping in your case here refers to the loss in energy of your oscillating system due to resistive forces such as friction and air resistance. So when your object oscillates and encounters friction or air resistance, work has to be done against those resistive forces. So that work has to come from something. It actually came from the energy of your oscillation. So if it came from the energy of your oscillation, that will in turn result in loss in energy of your oscillating system. Okay, so damped oscillations have amplitudes that tend to decrease exponentially with time, not linearly. So when we say that the oscillations have amplitudes that decrease exponentially with time, it means to say it follows a curve that looks like this. It doesn't follow a straight line. If your amplitudes were decreasing linearly, that would have meant that it follows a straight line like this, where your amplitudes would be at these respective points here. But it doesn't do like that, okay? It decreases exponentially. So that's just one thing to note. So if you're talking about damping, I'll just give the last two statements here. If you're talking about damping, there are actually three types of damping that you're supposed to learn. The first one is called light damping. Light damping is where oscillations are still maintained about the equilibrium position after the body has been displaced before the oscillations gradually stop. Okay, so the key thing here to note is that oscillations are still maintained about your equilibrium position. For damping, regardless of whether it's light, critical, or heavy damping, your amplitudes will still decrease with time. But how they decrease is different. That is what separates light, critical, and heavy damping. For light damping specifically, as its amplitude decreases to equilibrium, oscillations will still be maintained. On the graph that you have is actually represented by this red colored line here. This is what we meant by light damping. Your amplitude is decreasing to zero to equilibrium position, but is still oscillating. This is light damping. If you're talking about critical damping, your displaced body will return to the equilibrium position without passing through the equilibrium position in the shortest time possible. So critical damping here, it doesn't keep oscillating. It will just straight away go back to its original equilibrium position with the shortest time possible. That one will be represented by this blue colored line here. This is what we mean by critical damping. It doesn't maintain its oscillation. It just straight away goes back to its equilibrium position with the shortest time possible. Now, heavy damping is a bit similar to critical damping in that there's no oscillation about your equilibrium position. It will return to the zero displacement position, but very slowly. It happens in a longer time than that of critical damping. That one will refer to this green colored line here. It is trying to return back to its equilibrium position, but it does so in a very long time. So if I wanted to indicate out the time out, this one would be the time taken for critical damping, whereas this one would be the time taken for heavy damping. Okay. Now critical and heavy damping, the similarity between them is that no oscillation, no further oscillation is seen as object returns to equilibrium position. Okay, this is what damping actually is.